Okay, so to begin the week 4 lecture material, we're going to start on Monday with the signal levels. So in the signals that we have seen so far, we've commonly seen a stepped signal where there's a positive voltage for the indication of a binary 1 and a 0 voltage for the indication of a binary 0. But this week we're going to be moving on to looking at how different signal levels can be used to actually increase the efficiency with which communication occurs. So by communicating more than one bit on a single signal level, it's possible to actually increase the capacity of the network which is used. So we're more efficiently using the bandwidth which is available. So in part of this slides, we'll be appreciating the way in which the channel capacity is increased by increasing the number of signal levels. The signal levels are commonly to the power of 2. So we'll see that there may be 2 signal levels, there may be 4 signal levels, and so on. So we'll be thinking about how we increase the channel capacity using signal levels. And we'll also be looking at how to calculate the number of signal levels which we need to use in order to achieve a certain bit rate at the channel capacity. And if you remember back to week 1, where we talked about the Shannon theory to calculating channel capacity, this took into account both the bandwidth and the signal to noise ratio. But by increasing the number of signal levels, as we've said, we're increasing the effectiveness of the communication. We're communicating more information within the available bandwidth. So we'll be thinking about how we can actually calculate these signal levels that we need in order to achieve the bit rate at the channel capacity to maximise its use. So with regards to signal levels, as I said, we've commonly seen the step function where we have a binary 1 or a binary 0. So this binary approach to communication with regards to signal levels is a multiple level coding scheme. So the binary approach to signal levels is a multiple level coding scheme, and it's commonly limited to 2 levels. Whenever we talk about binary, we're talking about 2 levels in our signal. So these 2 levels represent a single bit symbol. So we either have a symbol which is representing a 1, or we have a symbol which is representing a 0. And where we see that the signal is moving upwards, we're representing the 1, and where it's along the base, this is representing a binary 0. So if we want to increase the number of bits represented by a single symbol, then we theoretically increase the capacity of the channel to carry the information by compressing more information into these symbols. So we're still working within the same overall bandwidth availability, but we're just communicating more information within each individual level, and this increases the efficiency of the communication. So what actually does this mean? So if, for example, we encode 2 bits into 4 symbols, okay, so we're encoding 2 bits, so for example 00, 01, 10 or 11, then each symbol change, so each time the signal changes, this represents 2 bits, okay, so every step of our signal change represents 2 bits of information. So as opposed to having 1 bit of information, as we've seen previously, we now have 2 bits of information. So you can see we're actually communicating more information within the same amount of bandwidth. This degrades the signal to noise ratio, okay, so this is a negative effect due to smaller signal level changes. So there's a smaller step between each signal level because we're using more signal levels within the bandwidth capacity. So this degrades the signal to noise ratio, which is a negative consequence. The more levels that we have, the smaller are the differences between them. Okay, so there's smaller differences between them, so the significant changes are smaller between them as well. So to actually contextualize what we mean when we talk about different signal levels, in the top figure we have a signal which is communicated using two signal levels. Okay, we've got two signal levels, and we have our 0 voltage, which is representative of a binary 0, and then we have our increase in our voltage to represent a binary 1, and we're using our two signal levels in order to communicate the two different bits of information which can be sent across the channel. So we can contrast that with a scenario where we've got 4 signal levels. So we've got 1, 2, 3, and 4, and each signal level is communicating 2 bits of information. So these ones are the same. So they're communicating the same 2 bits of information. So with each change in our signal level, we're actually representing double the amount of information. As another example, again, we have our 2 signal levels here, our 2 signal levels which are indicating the different binary digit that's being communicated each time. In another example, we have 1, 2, 3, 4 signal levels again. So we've got 4 signal levels which are communicating 2 bits of information each time. Okay, so it might seem that symbol encoding would benefit in both the utilisation of the available bandwidth and the energy per bit used to transmit the data. So symbol encoding may be seen to increase the utilisation of the bandwidth which is available and make it a more efficient communication. However, there are restrictions in the physical world, and noise limits the extent to which this is possible. So whenever we were calculating our channel capacity using the Shannon formula, if you remember that we took into account the signal to noise ratio. So whenever we're talking about our utilisation of the bandwidth with regards to signal levels, again, we have to think about the signal to noise and remove from our channel capacity the effect of signal to noise so that we can work out our overall channel capacity and the way it may be used most efficiently with a variable number of signal levels. So our Shannon capacity theorem, we saw in week 1, describes a theoretical limit. So this is the ideal limit for a given communications channel in order to carry information. So it takes into account both the bandwidth and the signal to noise ratio. Our channel capacity is the maximum amount of data which may be transmitted, measured in bits per second. And we also take into account here our bandwidth, so our available bandwidth in our network. So in relation to our available bandwidth and in relation to our signal to noise ratio, we can determine what is the overall channel capacity. So signal to noise is a division of the average received power in relation to the noise interference power. Okay, so it's the relationship between the received power of the signal in relation to the noise interference. So by improving the signal to noise or the bandwidth, we can carry more information. So if we reduce the amount of traffic that's lost through a signal to noise, the high signal to noise ratio, or we allow the channel to carry more information through increasing the amount of bandwidth, then we can carry more information. But these are normally restricted. Okay, so the bandwidth is fixed in reality, and the only other variables that we can interfere with, if you like, are the signal power and the noise. Okay, so we have to manipulate our communication scenario in relation to the signal power and the noise in order to increase the amount of data which may be transmitted across the network. So we do this by coding our bits into symbols. So we make more efficient use of our bandwidth. We code the bits into symbols, and the amount of information which is communicated per state then increases. Okay, so we're coding more information into each symbol. The downside of this is that there can be a loss in the signal to noise ratio. So this is an important aspect now with regards to calculating the number of signal levels based on the relationship between our channel capacity, so the amount of information which may be communicated in a second, so we're measuring in bits per second, and also based on the relationship with our bandwidth, which is measured in hertz. So that 1 hertz is 1 cycle per second, so this is the amount of information which is actually transported in a second. So if we want to calculate how many signal levels can be communicated across the network, we want to think about the channel capacity and the bandwidth of our channel. So we have the two approaches to calculating channel capacity. We have the Shannon theory whenever we have the presence of noise in the network, and we also have the Nyquist formula, which applies when there's no noise in the network. So if you're asked in an exam to calculate signal levels, then you should know whether to use either the Shannon formula or the Nyquist formula, and that will depend on the presence of noise, of a signal to noise ratio. So the Nyquist formula is calculated based on the channel capacity, the bandwidth, and the number of signal levels. Okay, so our overall channel capacity is calculated in relation to our bandwidth and our number of signal levels. So by changing these signal levels, we can influence the effective channel capacity. Okay, so B is our available bandwidth and M is our number of signal levels. So in a couple of example questions which could be asked in your exam in relation to signal levels, what is the channel capacity if the bandwidth of your network is 1000 Hertz and there are 8 signal levels? So we know the bandwidth of our network and we know the number of signal levels, and we want to determine what is the channel capacity. So we're not presented here with any noise. So the approach that we use is therefore the Nyquist formula. So we have our channel capacity that we want to calculate. We have our network bandwidth and we have our number of signal levels. And we can calculate out that the channel capacity is 6000 bits per second. Okay. So from this you can see that if we double the bandwidth in this scenario, it will result in a doubling of the channel capacity. Okay, so if we double this to 4000, for example, this will result in 12,000 bits per second. So whenever we're working with the same number of signal levels, we can increase the capacity by manipulating the bandwidth which is available, for example. But what's the effect actually of changing the number of signal levels? So in another example, if we have a bandwidth of 3000 Hertz and we double the number of signal levels from 8 to 16, what effect does this have on the channel capacity? Does this allow the channel capacity to also double? So in two scenarios, we have here our bandwidth of 3000 Hertz and we have our signal levels of both 8 and of 16. So because we've got no noise indicated, we can use our Nyquist formula and we can calculate the channel capacity for the two scenarios. So by doubling the number of signal levels, we can see that the channel capacity increased by 1/3. So we doubled our signal levels, but we didn't double our bandwidth. So the percentage increase depends on the initial value of M. So whenever we're thinking about how can we actually increase our channel capacity, this value for our signal levels is important in the way in which this is achieved. So remember, our bandwidth is fixed and it's the signal levels that we want to manipulate in order to increase the network capacity. So the Shannon-Hartley law applies in the presence of noise. So whenever we have an expression which includes some noise, we will be using the Shannon-Hartley law. and that's calculated based on the bandwidth and the signal to noise ratio. Okay, so our signal to noise, as a reminder, is the ratio between the signal power and the noise power. And remember that if we're presented with a signal to noise ratio in decibels, then we need to convert that using this formula into our signal to noise ratio. Okay, so there can be a number of steps that are involved whenever we need to take into account the presence of noise in the network. So as an example of a question which may be asked in this respect, suppose we have a spectrum of a communications channel which is 3 MHz to 4 MHz. Suppose also that the decibel version of the signal to noise ratio is 24 decibels. Okay, so first of all we need to convert our signal to noise ratio from the signal to noise in decibels. Okay, so using that information, we want to calculate the channel capacity overall. So we take into account our signal to noise ratio, so therefore we know that we need to use Shannon's theory. So our channel capacity, our bandwidth that's available in the network, our bandwidth is measured in terms of the spectrum of the communications channel between 3 MHz and 4 MHz, which results in 1 MHz. We want to convert our signal to noise ratio, which is measured in decibels, into the actual signal to noise ratio. So we plug in our numbers and we come out with a signal to noise ratio of 251. Okay, so we take our 251 of our signal to noise ratio and we apply that to our Shannon-Hartley law. Okay, plug those numbers in, so we have our channel capacity in relation to our bandwidth and our signal to noise ratio. 1 plus our 251, 252, and we calculate that through and we find that our channel capacity is 8 megabits per second. Okay, so if there was no noise in the network, how many signal levels would be needed to achieve this channel capacity of 8 megabits per second? So we've worked out what is our channel capacity, and now we want to work out how many signal levels do we need to achieve this channel capacity. So we're making an assumption in this scenario that there's no noise. We therefore use our Nyquist formula and we plug our numbers in. Okay, so we've got our 8 megabits per second, we've got our 1 megahertz channel, and we want to find our number of signal levels. And through calculating this out, we come to 16, so we need 16 signal levels in order to fulfill the channel capacity of 8 megabits per second. Okay, so this number of signal levels will always be a power of 2 in order to communicate our binary digits. And that's a conclusion to the slides on signal levels.